Galvanic cells. Galvanic cells take advantage of the fact that when some atoms get electrons, they release more energy than when other atoms do. And so if we take electrons from an atom like zinc that doesn't like its electrons all that much, and we give them to copper, an atom that likes electrons more than zinc, then we can get a gain in energy there, and that energy can allow us to produce electrical energy. So let's look at these two half reactions and think about how we can exploit this to produce energy. So copper is a strong oxidizing agent. That means it's really good at taking electrons from other atoms, or it really wants its oxidation number to be reduced, or it wants to oxidize something else. That's why we call it an oxidizing agent, because it oxidizes something else. Copper 2+, for example, is when it releases, well, let's not look at the specific amounts. Let's just say when it goes from copper 2+ to just copper, its chemical potential energy decreases by a large amount. The delta H is large and negative. It really likes those electrons. Alternatively, zinc, no atoms really like to be, oops, hold on, this should be 2+ here. No atoms really like to be oxidized. Atoms like their electrons, they don't just want to give them up for free. But zinc doesn't like its electrons anywhere near as much as copper would. So the chemical potential energy for zinc going to zinc 2+ would go up a little bit. So we have to pay a little bit of energy to make that happen. If I call this one 1 and this one 2, then the delta H for 1 is bigger than the delta H of 2. So when both of these processes happen together, the total delta H is still negative, which means there's still energy available to other forms. So this exchange of electrons is favorable. This is a strong exothermic process. This is a weak endothermic process. So overall, energy exits, and as a result is available to other forms. In a galvanic cell, we have these two reactions happen in different locations. We call each of these locations a half cell. So copper's half cell would have a piece of copper sitting in the liquid. It'd be attached to a wire. And within the liquid, which we would call an electrolyte, there would be copper ions. There'd have to be some sort of anion to go with it, like sulfate or something like that. So they'd be floating around and there'd be this piece of copper sitting in the liquid. On the other hand, in the zinc half reaction, there would be some zinc, usually some zinc in solution, but definitely some anions to go with it. And so these two reactions can work together to produce a difference in energy. Specifically, the copper 2+ ions here can come into the copper, and when they do, they will eat 2 electrons. So let's just say there's these electrons floating around and it's going to eat them and go into the copper. What this does is this creates a deficit or a lack of electrons as it's eating them all up. This cathode slowly grows and we get more and more solid copper, and more electrons get eaten, and we end up with a deficit of electrons, or a positive charge over here. Alternatively, this zinc, which isn't very good at holding on to its electrons, will jump out and become part of the solution. When it does, it will give up 2 of its electrons. Well, where are those electrons going? They can flow through the circuit and provide the electrons for the copper exchange. And so we've created an area with an excess of electrons that are given out in that reaction. And so we've created a negative end of a battery. We call the negative end of the battery the anode, and we call the positive end of the battery the cathode. And the way I remember that is that cathode has a T in it that kind of looks like a positive sign. So the electrons flow from the negative end of the battery to the positive end of the battery. Maybe if we want to exploit this, we have a light bulb or something like that in there, where we make them pay some of their chemical potential energy as they pass the light bulb and produce light or something like that we want, and get back to the copper, where the copper will eat those electrons and grow. The anode, getting eaten here slowly, gets worn out or gets used up over time. Now, if this is all we were doing, this reaction would stop very quickly, because despite the fact that copper wants those electrons more than zinc, and so it naturally makes sense for the electrons to travel through the circuit this way, the problem is that here we're using up the copper ions in the solution, and here we're producing zinc ions in our solution. So this solution is slowly becoming positive, and this solution is slowly becoming negative. What we need to do to keep that from happening is we need to add something called a salt bridge. A salt bridge is essentially a tube or something like that contains a bunch of ions. Some common ions that might be used are sodium nitrate or something like that. And what can happen then is that when these copper ions get used up, the sodium from the sodium nitrate salt bridge can move into this solution. Or the negative ions, who are getting repelled by the negative solution, can move up into the salt bridge. Alternatively, on this end, when these zinc ions are being produced, the nitrate ions can come out of the salt bridge to neutralize the extra positive ions in solution, excuse me, or the excess zinc ions can move into the salt bridge and account for the sodiums that are moving out on the other end. Either way, this salt bridge allows the charge to flow through the electrolytes and keep these two solutions neutral so they don't build up positive or negative. So slowly over time, the anode dissolves, releasing its electrons, creating excess negative charge. The negative charge is able to flow through to the copper. Alternatively, the copper, who likes those electrons more, is able to eat those electrons and make as a dissolved ion in the electrolyte, and it can jump into the cathode, causing the cathode to grow, and as a result we're getting a natural flow of electrons from an area with excess electrons to an area with a deficit of electrons, and as a result those electrons are going to a lower state of energy, and that energy is available to other forms like light. The charged ions in solution we call an electrolyte, and the bridge that keeps the charges from building up but allows them to flow from one solution to the other solution to allow both solutions to remain negative, we call a salt bridge. So that's how we make a galvanic cell, all built on the idea that, well, no atoms like to lose their electrons, and all atoms like to, if they are charged, gain electrons to go back to being neutral. Some atoms really like their electrons more than other atoms, and so we can exploit that difference to create an exothermic reaction and make energy available to other forms.